Lecture 2.11, Applications of the Lorentz Transformations. In the previous lecture, we derived the Lorentz transformations which transform coordinates in one reference frame, the O frame, to a moving reference frame, the O prime frame. We saw that we could write these equations in terms of t's and x's and v's, or make substitutions to write the equations in terms of CTs and betas. In this lecture, we'll look at several applications of how to use the Lorentz transformations. In this first example, we're going to see how time varies spatially in a moving reference frame. So we're going to start by synchronizing a set of clocks that are spaced distance L0 apart. All the clocks will be synchronized to the same time in the frame of reference of this platform. We're going to call this reference frame the O prime frame. Now this platform is going to be moving to the right with velocity v relative to the ground. So relative to the platform, the ground is moving to the left with a velocity negative v. We want to ask the question, what will these clocks read from the ground or O frame or O reference frame? So in the ground frame, the separation between the clocks is going to be length contracted. So the distance is going to be L0 over gamma as measured from the O frame. Because the clocks are equally spaced, we can write their position in the frame of reference of the platform as x prime equals to an integer n times L0. So when n is equal to 0, that's the center clock. The one on the right is going to be n equals 1, n equals 2, and then we'll have n equals negative 1, negative 2 to the left. We've seen that in the ground reference frame, these will be length contracted. So the positions in the ground frame at time t equals 0 will be in L0 divided by gamma. So that's the length contraction factor. Using the Lorentz transformation, we can write down what the time in the platform frame is going to be given the coordinates of our clocks and the time that we want to read them. So we want to read them at the time t equals 0, and we already see there, and we already have an expression for the position x. We can just plug in L0 over gamma here. This simplifies to minus n L0 v over c squared. If we cross multiply by c and replace v over c with beta, we get a simpler expression. So ct prime is minus n L0 beta. So for example, if the platform is moving to the right at half the speed of light, the gamma factor is 1.15. We set L0 equal to 1. Then ct prime is going to be n times 1 times 1/2. So in other words, minus n over 2. And now we can just write down what the times are going to be on our clocks. So when n is equal to 0, the time is going to be 0. As we increase our n value to the right, there's a negative sign here. So these clocks are going to be reading earlier. So minus 1/2, minus 1, and the clocks to the left will be reading later. So 1/2, 1, and so on. So we see that when viewed from a frame of reference that's in relative motion to the clocks, clocks at different positions are going to read different times. Okay, here's an example. Here's a little animation. So here again, we've got some clocks spaced evenly on this platform. Here's the time in the ground reference frame, the O frame. Here's the values on the moving platform. We're going to simulate this. We can see that the clocks are all ticking along. We can notice a few things in this simulation. So at time t equals 0, the center clock read 0. at time t equals 0, the clocks to the left read later times and the clocks on the right read earlier times. And as time evolves, the clocks tick on the moving platform more slowly than the one on the ground. So you can see actually right here, this clock right here on the ground reads time t equals 7, whereas that center clock reads 6.06. So not as much time has evolved on that clock than the one on the ground due to time dilation. Okay, so if you go back and replay this video a couple of times, look at what the initial readings of the clocks are and then the final readings, you should be able to answer a few questions. What's the velocity of the platform? What's the gamma factor? And how far apart are the clocks in the platform's frame? All right, so this will be a homework problem. See what you can come up with. It's worth noting that the Lorentz transformations can be written in a slightly different way, which is helpful for some problems. In this case, suppose that instead of looking at a single event from these two reference frames, that there's actually a pair of events. So each event has its own position and time values. We can calculate the displacements between the two events in terms of the x, y, and z components as well as the time component. Because Lorentz transformations are linear, we can simply replace the x's and x primes and t's and t primes with just the displacement values. So instead of x prime equals gamma x minus vt, you can replace it with these deltas. So this will be helpful in the next few examples. All right, next example, simultaneity. So given two events, say one event is at x equals 1 and ct equals 2, and the second event, x2 is equal to 5, ct2 is equal to 3. The question is, find the velocity of an observer where the two events occur simultaneously, and then in that frame of reference, what's the distance between them? So here's the solution. First, find the displacement between the events. So delta x is going to be, 5 minus 1, so 4. Delta ct is going to be 3 minus 2, or 1. We want the events to be simultaneous in the O prime frame, so that means that there's no time difference between them in that frame. So delta ct prime is going to be 0. So we can use this displacement version of the Lorentz transformations. We're going to set delta t prime to be 0 and then solve for v. So when we set this equal to 0, we can multiply the gamma into the 0 and just get delta t equals v delta x over c squared. That's where this came from. And then solve for v, so you get c delta t over delta x. Plug in the delta ct and the delta x values from here, and you get that the velocity must be a quarter of the speed of light. This is positive, so that moving frame would have to be traveling along the positive x-axis. Solution to part B, we want to find the displacement between the events in that moving frame. So we can use this Lorentz transformation equation. We want to solve for delta x. The gamma factor is given by this. Since v over c is 1/4, plug it in, then the gamma factor is going to be 1.033. We know that from before that delta x, remember, was 4, and c delta t was 1. So here we divided by c to make this v over c is 0.25, and then c delta t is 1. Plug that in, we get 3.87. So remember that the displacement between the events in the rest frame was 4. So in the frame of reference that's moving to make them simultaneous, they're a little bit closer together. They're at 3.87 meters. In this next example, we're going to derive the equations for time dilation from the Lorentz equations. So the question is, we want to find the duration of ticks on a clock in the moving frame O prime as viewed by an observer in the ground frame O. So we're standing here on the ground. We want to see how long one tick takes on this clock that's in this moving reference frame. So if you have a person riding along on the platform, they're moving with this clock. That means that the ticks on the clock here occur at the same location. So the displacement, the spatial displacement between the ticks here is going to be 0. So delta x prime is 0 for somebody riding along on the platform. For this reason, the person riding along on the platform will measure the proper time because, again, the clock will be at rest with respect to them. So delta t prime is going to be delta t naught in our previous notation. The time-dilated value will be just the displacement between the ticks as measured in this frame, so it's just delta t. So we pick the Lorentz transformation with these quantities, delta x prime, delta t prime, and delta t. That's this equation. We plug in the values, so delta t prime is just delta t naught. Delta x prime, we said, was 0. So we simply get that delta t is gamma delta t naught. So this is the time dilation equation we derived before, and so that checks out. You could do a similar thing for length contraction. This will be left as a homework, but basically you can go through a similar kind of calculation to derive the length contraction formula from the Lorentz transformation, so I'll leave that to you. This last example is a little bit longer. We're going to derive the Doppler effect equations from the Lorentz transformations. So we imagine that Oscar is standing here on the ground. Olivia goes flying past him at half the speed of light. So you can imagine that, say, Olivia's turn signal is on. So it's flashing once a second on the back of her motorcycle. The light waves from that flashing are going to take some time to reach Oscar. The question is, what is the time between flashes as seen by Oscar? And this is going to vary depending on whether Olivia is driving towards him or away from him. All right, so we're going to use the Minkowski diagram to kind of motivate the reasoning here. So here's a Minkowski diagram. The gray curves are in Oscar's frame, so x and ct. Since Olivia is driving past him at half the speed of light, this green line is the ct prime axis, and so it has a slope of 2, 1 over beta. We're going to overlay the coordinate grid for the O prime frame. So these lines are at constant ct prime, and these lines are at constant x prime. So if Olivia sends a signal once a second, then the events where her flasher goes on are just going to be at the integer positions along the ct prime axis. Okay, the time at which the signal is sent, as measured by Oscar, we can just take these events and read straight over onto the ct axis. This is just time dilation. So the delta t, the time that's elapsed on Oscar's clock compared to Olivia's clock, is just given by the time dilation equation. So delta t is going to be 1, and so these delta t's are just going to be gamma times, or just going to be gamma. So it's going to be gamma, 2 gamma, 3 gamma, and so on. Okay, but to see the flash, Oscar must wait for the light to travel from Olivia to him. So when that first flash occurs at Olivia's bike, she's going to be a distance v times t1 away. So remember that according to Oscar, the time of the flash is going to be t1. Since Olivia is traveling at a velocity of v, she's just going to be v times t1 away. So that distance is vt1. the time it takes the light to travel that distance is just going to be the speed of light times vt1. So what we see is that the total time it takes for Olivia's blinker to wait one cycle to flash is going to be t1, which is gamma delta t prime, plus the time it takes the light to travel back to Oscar, which is c v gamma delta t prime. We see that the total time it takes to go from here up to Oscar seeing the flash is given by this. And here's a little diagram showing when Oscar sees the flashes from Olivia's motorcycle. Notice that these are multiples of this first interval. So if you take the time from here to there and then double it, that's going to give you that next flash, and then triple it, that'll be the next one, and so on. Okay, so let's simplify this equation a little bit. So you can pull out a gamma delta t prime from both terms, leaving a 1 plus v over c. Gamma is 1 over square root of 1 minus v squared over c squared. Let's include the 1 plus v over c inside the square root. So this becomes squared when you pull it inside the square root. And 1 minus v squared over c squared can be expanded to 1 minus v over c times 1 plus v over c. Notice that this term, 1 plus v over c, is the same as the top one, so this term cancels 1 on the top, and you can simplify it into the square root of this ratio. So this is the final answer, and that the time between ticks on Olivia's bike is equal to the time between ticks as she measures it times this factor, 1 plus v over c divided by 1 minus v over c, where v is a positive number. She's heading away from Oscar. So if she's traveling at half the speed of light, you plug in 1/2 here, you get the square root of 1.5 divided by 0.5, and that turns out to be 1.73 times however long the blinks are for her. So if the blinks are 1 second apart, according to her watch, Oscar will see them being 1.73 seconds apart. So they're taking longer. Olivia is like traveling away from Oscar. It's going to take long. There's going to be more time between the blinks in Oscar's frame compared to Olivia's frame. So we've just seen the result in the case where Olivia is moving away from Oscar. Let's look at the case where she's moving toward him. So we're going to define Oscar. Oscar's still going to be at the origin. We're going to put Olivia at negative x values, so she'll be kind of moving towards him. We're going to define time t equals 0 as the time when Olivia reaches Oscar. So that's going to be this point here. So the x-axis is here. This is time t equals 0. When Olivia is still to the left of Oscar, these are going to be negative times, thus the negative signs here. So t1 is going to be the time of the last flash on Olivia's bike before she reaches him. So we go through the exact same calculation. We're going to simplify this expression. Notice the only thing different is we have a negative sign here instead of a positive sign. And that's because Olivia is actually moving towards Oscar in the period that the light wave is traveling instead of moving away. So before, Olivia was moving away from Oscar, so it was taking a little bit longer for each flash. Now Olivia is moving towards Oscar, so it's going to reduce the amount of time that Oscar has to wait. Okay, so anyway, you got this 1 minus v over c term there. Do the same thing. You expand gamma as 1 over v squared over c squared. Bring them 1 minus v over c inside, but now it's the 1 minus v over c term that's going to cancel with this one. So what we get is kind of the inverse of what we had before. So when Olivia is moving towards Oscar, it's 1 minus v over c over 1 plus v. instead of 1 plus v over c over 1 minus v over c. So it's just like the inverse. So in this case, when Olivia is traveling at half the speed of light, the time between ticks as measured by Oscar is going to be faster or shorter than the time on her clock. So it's going to be 0.577 seconds instead of 1.7 seconds. Now this is kind of interesting. Remember that according to time dilation, the value on Olivia's clock is always going to be ticking slower than Oscar's clock from Oscar's perspective. But because with the Doppler effect, we're actually we're taking into account the fact that light has to travel from Olivia's clock to Oscar, that's why it can look like the time between ticks on the clock is actually compressed instead of lengthened. Okay, so here's like a little summary. So when Olivia is moving towards Oscar, we see that this is the equation for the Doppler shift. The time between ticks is going to be less than the time on her watch. When she passes him, now she's moving away from Oscar, and the time between ticks is going to be greater. So if you thought about, instead of ticks on her flasher, if you thought about shining a light with a certain color towards Oscar, the waves are going to be compressed when she is coming towards Oscar, and so this is called blue shifted. So here in this little diagram, here's the object that's in motion. Since the object is kind of trying to catch up to the light waves, the wavelength of the light ahead of the moving object is going to be shorter or shifted towards the blue end of the spectrum. If the object were over here behind the moving object, the object is moving away from those waves, so they'll be stretched out and they'll be shifted towards the red end of the spectrum. Okay, so that's it for the Lorentz transformation examples.